In the last lecture, we learned how to use the Laplace transform to change the format of a function of time, from a function f of t to a function big F of s. We'd also like to be able to go the other way, to go from the Laplace transform of a function back to the original function. That is, we'd like to do an inverse Laplace transform. Now, unfortunately, there is no integral formula that we can use like we did for Laplace transforms. So what we're going to have to do instead is to use our table of Laplace transforms in reverse. So let's look at an example of what I mean by that. So here we've got our table of Laplace transforms here. Instead of going from a function of t to a function of s, we're going to be going the other way. So the trick here is going to be to identify what function in this table here our function in question looks most like, and then to find the function f of t then that corresponds to that. So in other words, we're going to be starting on this side of the table, the right hand side of the table, and then moving to the left hand side. Let's take a look at example 1. So here we're looking for the inverse Laplace transforms of these functions. So function 1, or function a, is the function big F of s is equal to 4 over s minus 2 plus 1 over s squared plus 9. Now, let's take a look at the first piece here, 4 over s minus 2. What function does that look most like in the right-hand side of our tables? Let's take a look. So scanning down the column here, we see that it looks most like this function right here, 1 over s plus a. So 1 over s plus a has the inverse Laplace transform of e to the minus at. So our task will be to rewrite our function so it looks like that and then go backwards. So again, we're going to rewrite this first part of the function so that it looks like something like 1 over s plus a. But in this case, of course, I've got a minus 2, so that's s plus minus 2. And so we're going to be able to take the inverse Laplace transform of that quite easily. Let's have a look at the second piece, 1 over s squared plus 9. Again, let's go back and take a look at our tables. So 1 over s squared plus 9 looks the most like this function right here. So we notice that that's of the form b over s squared plus b squared. We had 1 over s squared plus 9, so obviously b here is going to have to be 3. But I don't have a b on top, so what I'm going to have to do is multiply and divide by b. So I'm going to write this as 1 over 3 over s squared plus 3 squared. Again, what we've done there is identify that this piece here looks most like b over s squared plus b squared. So that's s squared plus 3 squared. So b is equal to 3, and of course I have to have a b in the numerator as well. And I got that in there by dividing and multiplying by 3. Okay, so now the inverse Laplace transform of this will be a function f of t. We can write that as a curly L again, with a minus 1 in the top right hand corner, a minus 1 superscript. So what we mean by that is that this is the inverse Laplace transform. It cancels out a Laplace transform. So I'm looking for the inverse Laplace transform of this function big F of s. And we've seen that the inverse Laplace transform of 1 over s plus a is e to the minus at. And I had a was equal to minus 2. Plus 1/3. Looking up our tables, we saw that 1 over b over s squared plus b squared became sine 3t. So tidying that up a little bit, we see that the minus signs cancel out. we get 4e to the 2t sine 3t. Let's take a look at the next example, B. We're looking for the inverse Laplace transform of the function 3 over s minus 12 over s squared plus 2 over s to the power of 5. Okay, so once again what we're going to do is we're going to go back and look at the tables and see if we can identify what functions look most like the functions that we have. So here I've got 3 over s, I've got 12 over s squared, and I've got 2 over s to the power of 5. So we can see that the functions that are most like the ones that we have are 1 over s squared, and m factorial over sm plus 1. And those are going to correspond to the functions of t, 1, t, and t to the power of m. So these are the 3 entries in our table that we're going to make use of. So we can see that we can now rewrite our function so it looks like those entries. This is going to be equals to 3 times 1 over s minus 12 times 1 over s squared plus 2 over s to the power of 5. Now remember that the Laplace transform of m factorial, the Laplace transform of t to the power of m was m plus 1 factorial over m factorial over sm plus 1. Might as well write that down so I remember it. So we have the Laplace transform of t to the power of m is equal to m factorial over sm plus 1. So what we've got to do is now compare this expression here with the expression that we have. It was 2 over s to the power of 5. So you can see by comparing the powers here, I've got sm plus 1, I've got s to the power of 5, so that these two guys here are going to give us that m is equal to 4. m is equal to 4. So I don't have that 4 factorial on top. I'm going to have to stick that in by, again, multiplying and dividing. So let's do that. We've got a factor of 2 that I have to keep. I'm going to multiply and divide by a factor of 4 factorial, so 1 over 4 factorial times 4 factorial over, and I'm going to rewrite s times to the power of 5 as s to the power of 4 plus 1. And now this piece here looks exactly like my expression in my tables, m factorial over sm plus 1. So you can see that m is going to be 4, and the Laplace transform, the inverse Laplace transform of that, is going to be t to the power of 4. One last thing that we need to do, of course, is to figure out what 4 factorial is. So 4 factorial is equal to 1 times 2 times 3 times 4. You may have a button on your calculator for that, but 4 factorial is equal to 24. So let's stick all that together. We've got that f of t, which we're writing as the inverse Laplace transform, curly L to the power of minus 1, or raised to the minus 1, of big F of s, is going to be equals to 3 times the inverse Laplace transform of 1 over s, and we saw that that was the constant 1, minus 12 times the Laplace transform of 1 over s squared. We saw that that was equal to t, plus 2 times 1 over 4 factorial times the inverse Laplace transform of 4 factorial over s to the power of 4 plus 1. So that's going to be plus 2 divided by 24, there's our 4 factorial, and the inverse Laplace transform was t to the power of m, with m equals to 4. So now we can tidy up a little bit. This is going to be equals to 3 minus 12t plus t to the power of 4, all divided by 12. So notice, of course, that we're trying to make our functions look as much like something on the right-hand column of that table of Laplace transforms as possible, and then using the table to go backwards to calculate the inverse Laplace transform. Now, there's not always going to be an easy correspondence between the left-hand side and the right-hand side. And in order to find the inverse Laplace transforms of a wider array of functions, we're going to have to introduce a very useful little function called the Heaviside function. So we're going to define the Heaviside function, u of t, in the following way. It's going to be equal to 0 whenever the argument t is negative. It's going to be equals to a half whenever t is equal to 0, and it's going to be equals to 1 whenever t is greater than 0. This is sometimes called the step function for reasons that will be obvious when we graph this function. So let's draw what this function actually looks like. Here's our t-axis. Now I'm going to include both positive and negative values of t, even though, as we've seen, when we're dealing with Laplace transforms, generally we're focusing on functions with a positive value of t. But we're being a little bit more general in our definition here. So let's see what the function u of t looks like. So we've said that the function u of t will take the value 0 whenever t is negative. So everywhere on the left-hand side of my line here is going to have a value of u equals to 0. So I can just fill this in as 0. And I'll use a little squiggly line just so I can see it above the axis itself. Now we need to see what happens at t is equal to 0. So let's mark where we're putting t equals to 0. At that point, it jumps up to the value half. So that's a half. And then after that, for positive values of t greater than 0, our function u is going to be equals to 1. And so that's going to continue off to infinity. Now we need to decide exactly what's happening at this point close to t is equal to 0. Because for this to be a proper function, it can only have one value of u for each value of t. As you can see, we've already assigned that this function u has the value 1/2 at t is equal to 0. So the lines at t is equal to positive numbers and t is equal to negative numbers, that is when u is equal to 1 or 0, those are not including the value at t is equal to 0. I'm going to indicate that with open circles. So you can see that our function now is a well-defined function. It's 0 for all negative values of t, it's 0 for all values of t on the left-hand side of the axis. It's a half right on the value t is equal to 0, and it jumps up to 1 on the right-hand side of the axis. You can also see that it only has one value for u at the point t is equal to 0. These are open circles, but there's one closed circle right there. Now, I've been a little bit careful there to define exactly what the value is, but for our purposes, in fact, it's not going to matter too much that the definition of the Heaviside function, or the step function, is a half at t is equal to 0. So we're actually going to make a little bit of a looser definition, and we're going to just set u is equal to 1 when t is greater than or equals to 0. In other words, I'm going to move this point at a half up to 1. Let's sketch what that looks like. So here's my t-axis and my u of t. Once again, u of t is defined to be 0 when t is a negative number. So I'm just going to indicate that with a squiggly line along the axis so I can clearly see it. I'm not including the value at t is equal to 0, and then I'm going to jump right up to 1. So I'm putting a closed circle to indicate that I'm including that point, and then I continue on for all positive values of t. Let's put in our axis values. So this is t is equal to 0, and this is the point u is equal to 1. So you notice that the only difference between these two graphs here is that I've swapped the point at a half up to this point here. Once again, it's well defined so that I only have one value at t is equal to 0. For negative values of t, or to the left-hand side of the axis, it's equal to 0, and for positive values, it's equal to 1. Now you can see why we call it a step function. U is sort of suddenly jumping up to the value 1 at t is equal to 0. So you can see that this is a really useful little function for dealing with functions that are discontinuous in some way, that have sudden jumps in them. Now, it's not all that useful to have u of t defined in this way because it's only for values at t is equal to 0 that we have the jump. We'd like to be able to move the jump around so that we can model more general functions. So let's introduce a slightly different version of the Heaviside function. It's a Heaviside function where the jump occurs at a point t is equal to c. So we're defined as u of t minus c. It's going to be 0 for t less than c, and it's going to be 1 for t greater than or equal to c. Notice that this is actually exactly the same as the definition that we've just given, because when t is less than c, the argument t minus c will be negative. When t is smaller than c, this is going to be negative, and we've seen that u of a negative value is equal to 0. Likewise, when t is greater than or equal to c, t minus c will be positive, and so u of a positive value will be equals to 1. So it's actually just exactly like the definition we've given, except it's a little bit more general because it allows us to have this sudden jump at t is equal to c. So let's sketch what this thing looks like. So here's our axis t, and here's the point t is equal to c. Notice that it doesn't have to be 0 anymore. And for all values of t smaller than c, that is all values of t to the left-hand side of c, we have our step function is equal to 0. So we've got a bit more scribbling to do this time. Once again, we're not including that point at t is equal to 1 instead, or t is equal to c. So at that point we jump up to the value 1. So that's the value 1 right here. Now one little note here, notice that I did not draw a vertical line. You might be tempted to do that when you're sketching these functions to make it a little bit more like a step function. But remember, a vertical line would mean that this function is defined to have all values between 0 and 1 at the point t is equal to c. That's not a well-defined function. Our function can only have a single value for every value of t. And by having this closed circle, open circle notation, I've guaranteed that this function is well defined at the point t is equal to c. Now, the nice way to think about this function is as a switch, that we're sort of switching something on. So for example, we could think about the voltage on a particular wire suddenly switching on at a particular time, or we could think about a stock jumping in price. So we're sort of switching things on. So let's have a look at some examples of this function, because it's going to be very useful and we're going to use it again and again in this topic. So let's try and sketch the function y is equal to 9 times the Heaviside function u t minus 4. So just take a look first of all at the piece u t minus 4. We can see that this is going to be a switch, and it's going to be equals to 0 when this argument is negative, and it'll be 1 when the argument is positive. That is, when t is less than 4, this will be 0. and when t is greater than 4, this piece here will be 1. So we can write this as a piecewise continuous function. That is, we can use the sort of open curly bracket notation to draw what, or to indicate what the value of this function will be in the different parts of the t domain. So we know that when t is less than 4, this argument will be negative, so that my heaviside or my step function will be 0. So 9 times 0 is 0. So this function will be 0 when t is less than 4. When t is greater than or equals to 4, my argument here is positive, so my heaviside function is 1. It takes the value 1. So I've got 9 times 1, so I get 9. So we can sort of read these heaviside function expressions as this telling us where the thing switches on, and this number here tells us what the magnitude of that will be. Let's sketch what this looks like. So it's going to take a value of 0 up until the point t is equal to 4. Let's break out our scribbly line again. 0, 0, 0, 0, 0, 0, 0. Don't include that point, and then it's going to jump up to the point, the value 9. So we'll indicate that on our y-axis. And it has the value 9 for the rest of eternity, right, all the way to infinity. Let's take a look at a property of the heaviside function that's going to really help us when we're dealing with Laplace transforms. In other words, let's take a look at the Laplace transform of the heaviside function, see what it looks like. We're going to do this from the definition, and it is given in your tables, but it's good to see it from first principles as well. So the Laplace transform of u of t minus c is equal to the integral from 0 to infinity of e to the minus st of our function, which is u of t minus c dt. Now notice that our function u of t minus c, our heaviside function, really sort of splits up our domain into values of t less than c and values of t greater than c. So we're going to take advantage of that by dividing up or splitting up our integral into two pieces. An integral from 0 to c, and an integral from c to infinity. Remember, we're always free to split up integrals into sub-integrals, if you like. Integral from 0 to some intermediate point, and then that intermediate point to infinity. Now the reason that I've done this is because we can see that the heaviside function u of t minus c, when t is between 0 and c, when it's in this interval here, we're going to have the heaviside of a negative value, right? T is less than c, so t minus c will be negative, so u of t minus c will be equals to 0. So this will be equals to 0 for this integral. So this integral is just going to go away. On the other hand, for this integral here, what is the value of u of t minus c when t is between c and infinity? Well, t is bigger than c, so t minus c will be positive, so our step function, our heaviside function, will be equals to 1. So that integral is going to live on. So we've got the integral from c to infinity of e to the minus st times 1. So that's an integral we can do. We've got e to the minus st divided by minus s, evaluated at c and infinity. So we've got, looking at that separately, we've got minus e to the minus c times s t over s when t is equal to infinity. And you can see that when I substitute t is equal to infinity in here, I've got e to the minus s of t. So this function is decreasing with increasing time. So that's going to go to 0. E to the minus a really, really big number. On the other hand, I've got this piece here, the lower limit of integration, e to the minus, so I'm going to get minus of minus e to the minus c times s all over s. So that gives me e to the minus cs over s. So this is a really cool result, because what it means is that the Laplace transform of a Heaviside function, or any discontinuous function at all, is actually a continuous function. This is a continuous function of s. This is the key to why Laplace transforms are so useful. They allow us to transform functions that are discontinuous into continuous functions, so we can play around with them to our heart's content. Let's now use this idea to calculate the Laplace transform of a Heaviside function that we've already seen in example 2. So this is the Laplace transform of 9 times u of t minus 4. So once again, we're going to make use of the fact that the Laplace transform is a linear operation. It doesn't care about that 9 in front. So the Laplace transform of 9 times the Heaviside function is going to be 9 times the Laplace transform of the Heaviside function. So that's going to be e to the minus cs. In this case, c is equal to 4, all divided by s. So we've seen that we can use the Heaviside function to represent sudden switches, sudden switching on of a function, for example. In fact, we can use this to build up other kinds of discontinuous functions. Let me show you what I mean. So we have a function f of t is equal to 1 when t is between a and b, and it's equal to 0 otherwise. So everywhere outside of that interval, a to b. Let's first of all sketch it, and then we'll look at how we can represent this function as a Heaviside function, or a combination of Heaviside functions. So let's sketch what this function looks like. So we know that this function is going to be equals to 1 between t is equal to a and b. Let's just assume that a and b are positive numbers. And from the definition, it's clear that b has to be bigger than a. A is less than or equals to t, less than or equals to b. So t is a value somewhere in this range here. We know that this function takes the value 1 between a and b. And it's equal to 0 outside of that. So we'll indicate that with squiggly lines, just so we can see it above the axis. Now, of course, we've got to decide what happens at the discontinuous points a and b. So what I'm going to do is I'm going to define this. From the definition, we see that the value f is equal to 1 is included. See those less than or equals to, less than or equals to. So those are included. It's very important to read the definition of the function carefully. It will tell you what to do at the discontinuities. And so I can't include those points at a and b when the function is equal to 0. So you can see that this function is 0 for a long, long, long time. Then it jumps up to 1, and it stays at that value, and then jumps back down to 0. So it's a sort of a switch on, switch off. And that's, in fact, that's what I'm going to call this combination. A switch on, switch off. So this is going to be really useful for defining functions that are discontinuous, that are 0 for a long time and then suddenly appear and then go away again. So let's see what the Heaviside function representation of this switch on, switch off function is. So what I'm going to do is write this as f of t is equal to u of t minus a minus u of t minus b. So notice that this is the combination of two Heaviside functions. One function that switches it on at t is equal to a, and one function that switches it off again at t is equal to b. I'm going to show you that these combined Heaviside functions give us exactly this switch on, switch off behavior. And the way that I'm going to do that is by looking at this function as a piecewise continuous function. That is, I'm going to split up the possible values of t into the different ranges, the different values of t, and then figure out what this function expression should be. So let's look at the three different possibilities. I've got t is less than a. I've got t is between a and b. And I've got t is greater than b. Those are the three different possible values of t that are relevant for this particular function. So let's take a look at what these combined Heaviside functions do in these different ranges. So for t less than a, let's take a look at the first of these two Heaviside functions. T is less than a, which means that t minus a is going to be negative. So u of t minus a will be 0. When t is less than a, it's also going to be less than b, because remember, a is less than or equals to b. So we're guaranteed that t is going to be smaller than b as well. So we've got t minus b is also going to be negative, so the Heaviside is 0 here. So this combined to give us 0. Now between a and b, I'm going to have t is bigger than a. So this Heaviside here will actually be positive, it'll be 1. But it's smaller than b. So this Heaviside will still be 0. So we get 1 minus 0 is equal to 1. Last one. We've got t is greater than b. So t minus a will definitely be a positive number because t is bigger than b and b is bigger than a. And t minus b will also be a positive number. So we're going to have 1 and we're going to have 1 for each of these two Heavisides. I get 1 minus 1 is equal to 0. So let's take a look at what the combined effect of these two Heavisides is. We can see that for t less than a, we have 0 because these two things are both 0. For t between a and b, the first one is switched on, but the second one has not yet switched off. So this is equal to 1 here. And then for t greater than b, I've switched on the first one, but then I've switched off again. So now I'm at 0. So you can see I get this switch on and switch off again. So it exactly reproduces the figure that we've shown here. So this is going to be really useful, this switch on, switch off combination of Heaviside functions. So you should definitely memorize this combination. We're going to use it a lot. So let's take a look at an example using this switch on, switch off function. Example 6. So our function is going to be equals to 7 between the values of t is equal to 3 and t is equal to 4, and it's going to be 0 otherwise. So you can see that this is exactly going to be a switch on, switch off. It's going to switch on with the value 7 at t is equal to 3, and it's going to switch off with the value 4 at t is equal to, with the value 7 at t is equal to 4. So let's express that now as a combination of Heaviside functions. So I'm going to write this as magnitude 7 multiplied by the switch on, switch off function. So that's u t minus 3 minus u t minus 4. And we can sort of read this as our function f of t is a function that switches on at t is equal to 3 with magnitude 7 and switches off at t is equal to 4. Now we can actually use what we've already calculated for the Laplace transform of the Heaviside function to figure out what the Laplace transform of this combination of Heaviside functions is. So the Laplace transform of this thing, again taking advantage of the linearity of the Laplace transform, I can write this as 7 times the Laplace transform of the first Heaviside minus 7 times the Laplace transform of the second Heaviside. Now let's refer back to our calculation of the Heaviside, the Laplace transform of the Heaviside function. So we did that in example 3. We did this from the definition, but in fact it's also in the table. So let me show you where that is. So our Laplace transform of the Heaviside is right here. Here's our Heaviside on the left-hand side, and here's its Laplace transform. So the Laplace transform of u of t minus c is e to the minus cs over s. So we're going to have equals to 7 times e to the minus 3s over s, in this case c is equal to 3, minus 7 times e to the minus 4s over s. So that's the Laplace transform of this particular function. You saw that we were given a function defined as a piecewise continuous function. It was given by its definition in different values of t. The first step was to transform that into a Heaviside function expression, taking advantage of this new switch on, switch off function that we've introduced. And then to find its Laplace transform, we used the Laplace transform of u of t minus 3 and u of t minus 4. So we're going to finish up the lecture by sketching a couple of different functions and seeing how the Laplace transform, seeing how the Heaviside function, can be used to simplify lots and lots of different kinds of functions. You can see then that we can use these ideas to find the Laplace transforms of quite a wide variety of different discontinuous functions. So let's draw my axes first of all. We're going to use these again and again, so we might as well copy that. And let's sketch what this first function looks like. So we see that it's going to be a function that is 1 up until the value t is equal to 3, at which point this thing is going to switch on. So it's useful here to actually split this up into its different values in different domains, and then from that figure out what this function should look like. So you can see that that Heaviside is going to cause a change in the value of the function at t is equal to 3. So it's natural to look at what the value of this function is at t less than 3 and t greater than or equals to 3. So we saw that when t is less than 3, this Heaviside is a Heaviside of a negative number, so it's equal to 0. So this thing will be 1 minus 0, it'll be equals to 1. But for t greater than or equals to 3, we saw that this thing is equal to 1, so I've got 1 minus 1, I've got this is equal to 0. So you can see that this is almost like the opposite of a Heaviside. It's more like a switching off. This is another useful little mini function that we can use to build up more complicated functions. So let's sketch this. We can see that this is going to be equals to 1 for values of t less than 3. And notice that I'm not really going to bother with negative values of t, because now we're really talking about Laplace transforms of functions for t greater than 0. So this is the value 1. And then it drops down to 0 at the value t is equal to 3. Now this is 3, and our function takes the value 0 for the rest of eternity. We can even indicate that with the little arrow there to see that's pointing towards infinity. Now, of course, we have to decide what happens at the value t is equal to 3. So let's take a look at our definition. Now this came from the definition of the Heaviside itself. It split up the domain for t into less than 3 or t greater than or equals to 3. And that tells us what values this function will take at t is equal to 3. So we've got less than 3 is at 1, greater than or equals to 3 is equal to 0. So at t is equal to 3, this thing is 0. So we're going to indicate that with an open circle up here and a closed circle down here. So let's take a look at our next problem. Again, this is a function involving a Heaviside function. So once more, I'm going to write this as a piecewise continuous function. So this thing will be equals to, let's divide up our domain into t less than 4 and t greater than 4. Or equal to 4. Looking at our Heaviside function, we can see that this is going to change the function at t is equal to 4. So when t is less than 4, that Heaviside is 0, and so the whole function will be 0. And when t is greater than or equals to 4, that thing will be equals to 1, and so the whole thing will be t squared times 1 is t squared. So what does this thing look like? Well, let's paste our little let's take a sketch of that. This thing is going to change at t is equal to 4, so let's put that in. Here's t is equal to 4. And it's going to be 0 up until that point. That's including the point t is equal to 0, but we don't have to worry about negative values of t. And then what's going to happen is that my function is going to jump up to the value 16. And the reason it's doing that is because at t is equal to 4, t squared is equal to 4 squared, it's equal to 16. And then it increases like t squared from there. So you notice that this is almost like a continuation of the function t squared, except that it's been cut off for values of t less than 4. In fact, we call this a cut. When a function of t is multiplied by u of t minus c, then it's going to look like that function, except it's cut off for values before that. Let me make this look a little bit more like t squared. So here's my t squared. And then for values of t greater than 4, it looks something like that. Now once more we have to decide what happens at t is equal to 4, and looking at the definition of our function, we can see that this is equal to 0 for values less than 4, so we don't include that point, and it's equal to t squared for values greater than 4, so we include that point. So we just have to be a little bit careful when we're defining our functions in a piecewise continuous way, that is, in terms of this little curly bracket and looking at the different domains, and being careful to look at where we have less than or greater than or equals to. And here I'm always guided by the definition of the Heaviside function that we're given, which is given by u of t minus c is going to be equals to 0 for t less than c and 1 for t greater than or equals to c. So we're going to use that we're not including the point on the left, but we're including the point on the right to guide us when we're drawing these figures. Let's take a look at part C. So this is f is equal to t minus 4 squared times u of t minus 4. So I'm going to again write this in its different parts of its domain. So you can see again that t is equal to 4 is the pivot point. It's the point where this function changes. So for t less than 4 and t greater than or equals to 4. And again, I'm using the definition of the Heaviside function to guide me on where I put the less than and where I put the greater than or equals to. So for t less than 4, that Heaviside is 0, so the whole thing is 0. And for t greater than 4, the Heaviside is 1. And so this thing is t minus 4 all squared. So what is that actually going to look like? Well, once again, I'm going to have 0 up until t is equal to 4. But the difference this time is that now I'm going to have not t squared, but t minus 4 squared, which is a shifted version of t squared. So it's going to grow like t squared, but it's been shifted to the right by 4. So the function t minus 4 squared connects with the value of the function at t is equal to 4. So we call this a shift plus a cut. I've got a cut in the sense that I've cut off all the values of this function before t is equal to 4, but it's been shifted so that it continuously changes. So I have it's 0 and then it grows from 0. So it's a shifted version of t squared. Last example, we've got t squared times u of t minus 2 times minus u of t minus 7. So again, I'm going to sketch what this thing looks like. But first I'm going to write out what this function is. So we've got 2 changing points this time. I've got values of t less than 2, values of t greater than 2 or equals to, and less than 7, and values of t greater than or equals to 7. And again, notice that I'm guided by the definition of the Heaviside function in terms of setting where I put my less than or my less than or equals to. So I've got the Heaviside is 0 between t is equal to 2 and 0. Between 2 and 7, this is equal to 1, this is equal to 0, and so on. So we can see that this thing will be 0 here and here, and it'll be t squared in here. So what I'm going to do when I sketch this thing is I'm going to sketch sort of in the background. Let's use a different color. It's going to be t squared. So this is my t squared growing with t. But it's only going to be filled in between 2 and 7. So let's put that here. So here's 2 and here's 7. And then outside of those values, it's going to be equals to 0. And just to indicate where these values are, this is e to the power, sorry, this is t 2 to the power of 2, which is 4. And this will be at 2 to the power of 7 to the power of 2, which is 49. So we can see that this is a sort of a switch on, switch off, but let's take a look at what happens at the discontinuities. So I'm not including this point, I'm including this point. I'm not including this point, and I'm including this point. So this is a little bit like the example we saw before, except I'm being a little bit more careful in the definition of what happens at my discontinuities. Notice that going from here to here, that is going from the definition of the Heaviside to this expression as a piecewise continuous function, can be a little bit ambiguous because we have to decide, we have to make a choice whether we're including the point on the left or the point on the right. But then when we go from the piecewise continuous to the sketch, there's no ambiguity anymore. These two have to be completely consistent. So you can see that my definition here, t less than 2 does not include that point, but it does include that point, t less than or equals to t. 2 is less than or equals to t. And likewise at 7, I'm not including this point, but I am including this point. So I just have to be consistent going from this expression, this form, to the sketch. But there is a small ambiguity going from this point, going from the Heavisides to the definition in terms of a piecewise continuous function. All right, let's take a look at example 8. We've got a function that we're going to try and express using a Heaviside, and then we're going to sketch it without the use of the Heaviside. So once again, I'm going to sketch this in terms of its different parts of the domain. So you can see that something's going to happen at t is equal to 1, something's going to happen at t is equal to 3. So those two change points are going to give me 3 different regions. So I've got f of t. I have to figure out what this thing is going to look like between 0 and 1, or just t less than 1. Of course, we're only again thinking about positive values of t. For 1 less than or equals to t less than 3, and for t greater than or equals to 3. And then we're thinking about which parts of this function get switched on at different stages. So you can see that this piece here, 3t, and this piece here, minus 1, those are always going to be there, no matter what. So even when I don't have this piece switched on or this piece switched on, when t is less than 1, these two pieces are still going to be there. So I'm going to have 3t minus 1. Then I come along and I hit t is equal to 1. So I'm between 1 and 3, which means that this piece is not yet switched on, but this piece has. So I've got 3t plus t minus 1. I've got 4t minus 1. Lastly, t is greater than or equals to 3. So now both of these pieces have been switched on. Both levers have been switched on. Both step functions. So I've got 3t plus 1 minus 1. So I've got 4t plus 1 minus 1. I've got 4t. That gives me all the different pieces now, and I can put that together into the sketch. So I'm going to divide my domain up into 1, and 3. Between 0 and 1, I've got 3t minus 1, so that's actually going to dip below the x-axis. It's going to have a slope of 3. Let's draw that a little bit shallower because I think I'm going to run out of space pretty quickly. There we go. And then between 1 and 3, this thing grows like 4t minus 1. So it's going to go like a little steeper. You see I'm having difficulty drawing these slopes correctly. do that. This is a bit steeper then. And then I've got this growing like 4t. So just in case those two things look a bit too similar, I'm going to write the slopes. So this is m equals to 3. It's 3t minus 1. This is m equals to 4. I'm talking about the slopes, of course, here. So this is 4t minus 1. And this is m equals to 4. It's 4t. So my drawing skills are not so great, that's why I became a mathematician. But I still have to be careful about how I define my discontinuities. So we've got less than 1 is equal to this one, less than or equals to, less than, and greater than or equals to. So that's going to indicate to me that I am not including this value, I am including this value too. I'm not including this value, and I'm including this value. So that gives me everything I need. Let's take a look at the last example. Example 9. So here we're actually given an expression in terms of a Laplace transform, 4 over s squared plus 3e to the minus 9s divided by s. We're going to want to take the inverse Laplace transform of that to find our function f of t and then sketch it. So to do that, we're going to have to take a look at our tables. So we can see that this thing looks like for 1 over s squared, and this thing looks like 3e to the minus 9s 1 over s. So that first term, 1 over s squared, that's one of our tabled Laplace transforms. So the Laplace transform of 1 over s squared is right here. So its inverse Laplace transform will be t. So we've got that the function f of t is going to be 4 times t. Now let's take a look at this other piece, 3e to the minus 9s 1 over s. Well, you see we've got an e to the minus 9s 1 over s, so let's take a look at our tables. See if we can spot something that looks kind of similar. You notice here that we've got an e to the minus cs over s is equal to our heavy side. So this is actually precisely the definition of the Laplace transform of the heavy side. So we can use e to the minus cs with c equals to 9. So we're going to have plus 3 u of t minus c, and c was equal to 9. So our function is defined as, in t world, is 4t plus 3u of t minus 9. So let's again just draw what that looks like, or write what that looks like in the different values of t. So we've got t is less than 9, and t is greater than or equals to 9. Again, I'm guided for the less than and the greater than or equals to by the definition of the heavy side itself. So for t less than 9, this thing will be 4t plus 0, and for t greater than or equals to 9, this will be 4t plus 3. So that extra little 3 is turned on at t is greater than or equals to 3. So sketching this, we see that things are going to change at t is equal to 9. It's going to grow like 4t up to that point, and then it's going to have a little jump up. It has the same slope for both pieces. So the expression for each of those is 4t and 4t. can also actually put in what the values of these functions are at these 2 points. I've got 4 times 9 is 36. And 4 times 9 plus 3, which is 39. And looking again at the definition, you see that I'm not including less than 9 and I am including greater than 9. So I can tell what to do at my discontinuity. Don't include that point. Do include that point. So that's what the sketch of the inverse Laplace transform of this function looks like. So we're going from a continuous function of s to a discontinuous function of t.